The second part of the core practical on investigating inks is chromatography, and it looks at chromatography as a technique to separate the dyes in a coloured ink. So we're going to take black ink and we're going to separate the colours that make up black ink. So the equipment that you need for chromatography is very simple. You need your chromatography paper, which is just a piece of filter paper, and you need your beaker that you're going to suspend your filter paper in. What you do first of all is you draw a line on your filter paper, and that line needs to be in pencil, not in pen, because you don't want it to smudge. And once you've drawn your line, you're just going to put 3 dots on the line at the bottom of the filter paper, and those 3 dots are the 3 black inks that we're going to separate. So I put my 3 dots onto the line that is a centimetre above the bottom of the filter paper, and then I'm going to suspend my filter paper in my beaker, and I'm going to fill it up with water. And it's really important that you get the height of the water correct. The water needs to be touching the base of the filter paper, but you don't want it above the line of the dots. If it's above the line of the dots will just smudge and run out into the water. You want the water to travel up the paper, so the paper's got to be in the water, but the dots have got to be above the line of the water. So if you've set your level up properly, what will happen is that the water will travel up the filter paper. And as the water travels up the filter paper, it takes the inks or the dyes from the ink from the 3 pens with it. Now, some of the dyes will travel further in the water than some of the other dyes, which will get left behind. And this effect separates the dyes into the different colours. So we can see here, black ink is actually made up of yellow, black and blue in this case. And this black ink actually had some pink, some black and some blue in it. Now, what is important to realise is that the black ink is a mixture of different coloured dyes. And what chromatography does is it separates that mixture into the different components or the different things that it's made out of. In this case, black ink is a mixture of different coloured dyes, and the black ink can be separated into those dyes using chromatography. In order to explain what's going on in chromatography, you need 2 terms. The stationary phase is what stays still, and in this case that's the filter paper, and the mobile phase is what's moving, which is the water. Now, the dye that travels the furthest likes the mobile phase, likes the water more than it likes the filter paper, and therefore it travels further up the paper. The dye that travels the least far likes the filter paper more than it likes the water, so it's held back by the filter paper and therefore it doesn't travel as far. Now, when you get your results from your chromatogram, you'll see that the colours aren't actually separated very well. They tend to smudge into each other, but you can see the individual colours that are present. The chromatograms that you're given in an exam question will show individual dots, and you'll get an individual dot for each dye in the ink. So if these were my results, and these 2 diagrams don't really match up, but what I'm trying to show here is that this ink, PM, only contains 1 dye. It contains a red dye, which is there. This ink E, contains 2 dyes. It contains a blue dye and an orange dye. And this ink S contains two red dyes, but they're different red dyes, and one is the same red dye that is in PM. So I can tell that the dyes are the same because the dots will travel the same distance up the filter paper. So I've included this chromatogram so that we can just have a look at an example of some of the results that you could get from chromatography. Now, this chromatogram looks at 6 different samples, labelled 1 to 6 down the bottom. So I've got 6 different inks, and I've got one sample which would be an unknown called S. And they might ask you questions about what ink S contains. Now, what this tells me is that ink 1 contains one dye. It contains a brown dye, and that is there. Ink 2 contains one dye, which is an orange dye. Ink 3 contains a red dye, which is there. Now, ink 4 is the first one that gets interesting because that contains 2 colours. So the number, if I go up from the number of dots that I get is equal to the number of dyes in the ink. And ink 4 has got a blue dye and an orange dye. And ink 5 has 2 red dyes. So it's red, but it's different from ink number 3. Although it has got one dye that is the same, ink 3 doesn't have the other dye that ink number 5 has. Now, ink number 6 is actually identical to ink number 1 because it's just got one brown dye in it. So by looking at the number of dots, I can tell how many dyes there are in my ink. By working along, I can tell whether the inks are similar to each other or whether they have the same dyes in them. So my unknown sample, S, I can say that it's got 2 inks, 2 dyes in it, a red one and an orange one, and the red dye is dye that's in ink number 3, and the orange one is the dye that's in ink number 2. So the last thing that we can do with our chromatogram is that we can calculate the value for how far the dots have travelled up the paper. And this is called the RF value. And each dot will have an RF value. And the RF value is the fraction of how far the dot has travelled up the paper compared to how far the solvent has travelled up the paper. So what I do is I measure with a ruler, and you might have to do this in an exam situation. You might have to actually use your ruler to measure how far the dots have travelled. So the red dot has travelled 6 centimetres up the paper, and I measure that to the centre of the dot from the start line. And the solvent has travelled 10 centimetres. So the RF value is always a fraction, and I just put the small number over the large number. It's always a number between 0 and 1, and so I just divide 6 by 10, and that gives me the RF value of the dot A, which is 0.6, and the RF value for dot B is going to be 9 divided by 10, which is 0.9. Now, the thing about the RF values, they're always a number between 0 and 1, and the closer to 0 they are, the least far the dot has travelled up the paper, and the closer to 1 they are, the furthest the dot has travelled up the paper. So just to prove that we've understood our work on chromatography, we've included this exam question. It says, some food colourings are a mixture of soluble coloured substances. Mixtures of soluble substances can be separated by paper chromatography. paper chromatography was used to try to separate the coloured substances in 5 food colourings V, W, X, Y and Z. Figure 3 shows the spots for the 5 food colourings on the chromatography paper at the start of the experiment. The paper was placed in a beaker with the bottom of the paper in the solvent. Number 1, identify the stationary phase in this experiment. Well, the stationary phase is the thing that doesn't move, and in this case it's the filter paper that doesn't move, so I think the best answer is filter paper. And the second part, give a reason why the spots of the food colourings must be above the level of the solvent when the paper is placed in the solvent. Well, the dots have to be above the water because the dyes have to be soluble in the water, otherwise they wouldn't move up the paper. But if they were touching the water, they would just bleed out into the water. So must be, well, the food colourings must be above the level so they don't dissolve into the solvent. The next part is again about solubility. It says figure 4 shows the chromatogram at the end of the experiment. Give the reason why the food colouring V has not moved. Well, if the dot hasn't moved, it doesn't mean that it's got one ink in it. It means that the ink is not soluble in the solvent. If you need to choose a solvent when you do chromatography that the dyes are soluble in the solvent. If you don't choose a solvent that the dyes are soluble in, then the dyes won't move. So the answer is the dye is not soluble in the solvent. The next part, explain by referring to figure 4 which food colouring contain the greatest number of soluble coloured substances. So the answer is Z. Which food contains the greatest? Because, and then because it says explain, you need a reason. Z, because it has the greatest number of dots. And the last one coloured food substance X moved 5.8 centimetres when the solvent front moved 6.6 centimetres. Well, the calculation that you need to do is distance at the smallest number over the largest number, 5.8 divided by 6.6, and that gives you a value of 0.87. Okay, remember I'm looking for a number between 0 and 1. The dots travel quite a long way up the paper, so the value is 0.87.